So we're going to talk about smooth muscle excitation, which is required for smooth muscle contraction. We can see that we have spontaneous depolarization, which results in activation of cation channels, and you get cation influx, which depolarizes the membrane. We have ability to stretch the smooth muscle. There are cation channels that are sensitive to that. Again, letting cations in, which depolarizes the membrane. And then you can see here we have GPCR mechanism, where a neurotransmitter, hormone, or other mediator can activate a GQ-coupled receptor here, which turns on the activity of phospholipase C, which cleaves PIP2 to IP3 and DAG. Remember that IP3 activates an intracellular ligand-gated ion channel. In this case, it's a calcium channel that lets calcium out. But also, we have the diacylglycerol and also the calcium that can activate this kinase PKC, which can then phosphorylate and turn off a potassium channel, which means you also get depolarization because potassium normally leaves through potassium channels. So closing that causes the membrane to depolarize. So in all of these cases, we get depolarization, and ultimately what that does is it activates L-type calcium channels, which are the important calcium channel found on smooth muscle, and these open with depolarization, and you can see that extracellular calcium now is going to go down its electrochemical gradient and increase the intracellular calcium. And in all of these cases, we get an increase in intracellular calcium. Now if we go and look at the smooth muscle contraction mechanism, we can see that this involves a myosin ATPase activity. Now, this myosin ATPase activity is set and determined by the phosphorylation status of myosin light chain, which is a protein that is associated with this myosin ATPase activity. So, really this activity, if you increase it, you increase contraction, and then if you decrease the myosin ATPase activity, you decrease contraction, which we can also say relaxation when we're talking about smooth muscle. Now, the level of the phosphorylation status of the myosin light chain protein, you could imagine, is going to be between the kinase that puts the phosphate on, which is myosin light chain kinase, or MLCK, and the phosphatase that removes that phosphate, myosin light chain phosphatase, or MLCP. So it's the back and forth between these two proteins that are doing opposite things. One's putting a phosphate on, the other one's taking the phosphate off. Depending on the level of activity of those proteins, that will determine how much phosphorylated myosin light chain we have. So if we want to look at this diagrammatically, we can see we're looking at contraction here. So there's our contraction that we want to get, and we know that we need an increase in the myosin ATPase activity, right? We want that to be high, and you can see what's biasing that towards phosphorylation is the myosin light chain kinase here, which remember puts on the phosphate. And you can see that the arrow's thicker here because we have more MLCK activity when we're talking about contraction. So MLCP, which removes the phosphate, has relatively lower activity when we're talking about the contraction mechanism for smooth muscle. And so we have less going towards the dephosphorylated state. So now how do we get this to happen? Remember all of those mechanisms we just discussed, which increase calcium, that causes a association with a calmodulin protein. You get a calcium calmodulin complex, and that activates the MLCK protein. And that's how increasing intracellular calcium results in an increase in contraction when we're talking about smooth muscle.